Hey kids, time for our last lesson of the semester. I can't believe it. Congratulations to all of you. In our previous video, we learned how to use the Gauss divergence theorem to translate a flux surface integral, which is a double integral of flux, into a triple integral of volume, right? Where all the divergence of F, right, contained within this in this shape. So you're kind of finding volume of divergence, kind of, sort of. Well, what if you want to use the Gauss divergence theorem to translate just a regular surface integral into a triple integral? Gauss says, I don't think so, right? This is a theorem. This is a theorem. You have to match the form of the theorem if you want to use it. So the handout that you have after today's lesson, number 1 through 3, practice what we did on day 1, which is I give you a flux surface integral, you translate it into a triple integral and evaluate. But number 4 and 5 are like this. I give you a regular surface integral and I ask you to do a prequel step so that you can use the Gauss divergence theorem to translate to a triple integral and then evaluate. So this is what we are going to do today. So given our handy dandy sphere, here's our unit sphere. I want you to evaluate this surface integral. All right, so again, that's something floating around here. You can't use the divergence theorem on that. Gauss says, I don't think so, unless your integrand looks like this. You can't use the divergence theorem. So my question is, though, can I transform this integral into a dot product? Kind of, sort of like factoring. So the first thing I did, I started with the normal. And I said I want to dot a vector field with a normal. So I took the normal of my surface and divided it by the magnitude of the gradient, right? So hopefully you can see where 2x, 2y, and 2z came from, and then the square root of all of those squared and added together. Look what I did here with the denominator, factored the 4 out. Do you see what this is? X squared plus y squared plus z squared. What can you replace that with? A 1, right? From up here. So I can factor the 2 out of my vector, and the square root of 4 is just 2. So that cancels out, and my normal is just x, y, z. So check. I have one of the factors, right? Factor, not really legitimately factors, but I think you kind of get where I'm going here. So I've taken x squared plus y plus z and said, is there a vector that if dotted with my normal, x, y, z, would result in x squared plus y plus z? Can you see it? Right? What could you dot with x, y, z to get the result, to get the given integrand? How about that? X squared plus y plus z. That's my integrand. Check. I have f dot n. Now Gauss steps aside, says, okay, now you can use the GDT. So let's take our now flux integral, wink, wink, and turn it into a triple integral where I use the divergence of my vector field, F. Where's my vector field? Nope, here it is. P, Q, and R. So that a divergence is just partial x with respect to x, partial 1 with respect to y, partial z, partial 1 with respect to z. So the divergence was 1. So my integrand of the triple integral by the GDT is just going to be a 1. So remember, I was asked to evaluate the surface integral, but I took the surface integral, said I didn't want to do it, created a normal. Then I could find the vector field F dotted with my normal to create my integrand. And now I am just integrating this triple integral with an integrand of just 1. So I took dv and broke it up into dz, dA, where here are my values of z, right? Going from negative, getting z by itself here. When I did that with an integrand of just 1, right, my intermediary step here was I had z to the first over z, evaluated that negative square root and that positive square root. So using the fundamental theorem, right, of the integral evaluation theorem, I ended up with, right, this radical minus negative of the same radical, which is where I got my 2 of these. I think you can see the polar happening. Going to go all the way around with my theta. The radius of that sphere was just 1. Paid the price, translating into polars, taking dA into polars, r dr d theta. So I'm going to move this 2 out. So I'm going to have my 2, and then I can separate, since I don't have any thetas in here, you know, you're just going to be integrating d theta from 0 to 2 pi, and I hope you figure out that's, you know, from experience, that's just 2 pi. So I've taken care of this. I've taken care of this. Now I have to integrate 1 minus r squared r dr. So u is going to be 1 minus r squared. du is going to be negative 2r dr, which means negative 1/2 du is equal to r dr. So now I'm going to have a negative 1/2 here times, I'm going to integrate u to the 1/2, right? R dr, which turned into negative 1/2 du. My u is 1 minus r squared to the 1/2, so I'm going to get 1 minus r squared to the 3/2 divided by 3/2, but that's really multiplied by 2/3. And that's going to be evaluated at 0 and 1. So 2 times this is 4 pi. Oh, cancel that out. So there I have a negative 2 pi here. And what do I have here? 2/3 times, plug in a 1. 1 minus 1 squared is 0. 0 to I don't care is 0. Minus, put in the 0. 1 minus 0 to the 3/2 is 3/2. So I end up with negative 2 pi times negative, whoops, sorry, that's a 1, times negative 2/3, which is what? What? 4/3 pi? 4/3 pi? Wait. Hey, what is the, whoa. Hey, I kind of expected that, didn't I? Here I was asked for, I was doing a triple integral, which is a volume of a sphere. And I've, with my integrand of just 1, this was 4/3 pi r squared, but what was the radius? 1. OMG. Math is so cool. Math is so cool. All right. So for the handout, some of the algebra and integration is a little hairy, so you might want to get started on it, but we will have some time. We'll do some examples in our live session of both types. And then we should have some time to start on this handout. And I will see you in our next live session.